Hello, everyone. Welcome back to today's lecture number 10, where we're going to talk about the second applications of the voting game model on the missing data imputation. The key question here is whether we can use the voting game as a more powerful replacement for the k-nearest neighbors imputer. The answer is yes, and we will see exactly why. So first, let's recall the connection between those two models. A KNN models is a missing data. It can be used as a missing data imputation tool by looking at the K. That's, for example, K equals 5. They will, for each missing point, they will look at their, let me write it down. So let's say this is a missing point. They will select the most closest instance. Let's say these are labeled 1, 1, 0, 1, 0. They will choose k nearest neighbors and perform the majority vote. In this case, there are three instances on label 1, so it's a majority, it will become 1. So how can our voting game model replicate this? In each in each case of the missing data, we'll consider them as all friends. So these are five different friends and the five only friends for the node in the middle. And we will make all the weight equals 1. So I'll not write it, but all the weight equals 1 to simplify this, right? And how can we do that? And so no repulsive neighbors, only friends. Every weight equals 1. And this should be the uppercase, sorry, uppercase, the ceiling of k over 2. So in this case, k will be equals to 5, and tall I will be equal to 3. So if you have 3 or more voting the same 1, it will become the 1. We can see that these replicate the KNN. So in a sense, KNN is a special case of our voting game model under these three assumptions. But in addition to that, the voting game model can allow more freedom in fine-tuning the model to make it better suited for each special case. So one point is that in the voting game model, the tall I is based on individual, right? So since we got this endogeneity of the tall I in the voting game model, it will have a lot more freedom on choosing it. And also, the tall I is discovered separately for each individual rather than being fixed globally. Secondly, repulsive neighbors. So in the KNN, you only choose K nearest neighbor, you got no repulsive neighbors. But a voting game model allows that, and it allowed enemy relationship to carry more informations, a point where whose neighbors consistently choose the opposite label can be informative. But KNN didn't take that into account. And third point is the joint imputation. Why it's joint imputation? Because KNN is doing this separately. You look at each missing point. For each missing point, you only look at the discovered neighbors. But our voting game models are treating all these neighboring points, sorry, are choosing all these missing points in one go, in the same time, at the same time. So it has more interaction between those missing points. And this last point is the most important aspect of this application. So let's go to the next slide. As I established before, how can we build the data? How can we build a network? In fact, what we have is for each instance that is known, it will be part of the prerequisite because you cannot choose that. It's a known. You have nothing to impute there. So x equals 1 for mandatory and x equals 0, it becomes forbidden. What is interesting are those missing features. We'll treat them as free choices, and they were going to be imputed by solving the mixed integer linear programming of our voting game model. And how about the network? Well, we can build a network by selecting this. As I showed you before, let me draw this. So let's say we got a missing point I. What is the network? Well, we will treat the data, we will calculate the k nearest neighbor, as the KNN suggests, and we create a network by setting them as friends. That's it. We got the choice of settings the farthest one as enemies. This will be part of the parameter. So this is the joint imputation mechanism. Every missing instance is an active participant in the solving process, not just a passive recipient of the majority vote from its observed neighbors. Let's look at the next slide. So to test whether this joint imputation matters, we need a realistic missing data scenario. Uniform random missingness is too easy for KNN that can almost always find an observed neighbor nearby. Instead, we decide to engineer clustered missingness in two steps. Step one, we pick 1% of the instance at random. We call them as seed points. And secondly, we mark all instances with a distance r to those instances as missing. So we randomly choose data as missing, and we will pick radius r and mark all the neighborhood as missing data. This process will produce specially correlated gaps that typically account for around 20% of the data set. So this is the mathematical way of saying that we pick those seed points and we pick all the instances j that are within a r distance around the missing point, the missing center, we can say. So why do we make it clustered? Clustering mimics real-world patterns, actually. For example, sensor failures, survey non-responses, and also demographic blind spots that all produce those specially correlated missingness, not the uniform holes around the data set, but correlated. It is also specially challenges KNN when all nearby instances are missing. Then KNN has no observed signal in the local neighborhood, and it can degrade badly. However, the voting game model benefits from clustering because those missing instances in the cluster can inform each other through the joint solving processes. So let's look at the result here. We compare using KNN and using the direct voting game model. Here are the accuracy results across all 6 UCI benchmark data sets, where the missing data are clustered, described as before. And we compare those direct voting game with the best KNN situation, sweeping K from 3 up to 15. So the voting results are here. So we got 4 data sets out of 6. In this case, the voting game model outperformed the KNN model. The 2 largest groups are tic-tac-toe and card evaluation. In this case, KNN wins on Monk 1 and Monk 3, those data sets have weaker clustering structure, so the joint imputation advantage shrinks and standard KNN competes on equal footing. So the conceptual reason for the gain is that the network effect. Of the network effect. Look at the left column here. When we have the standard KNN, we impute each data independently. We use a fixed K. We cannot use enemy signals, and missing neighbors are reducing those accuracy. But for the voting game model, we impute everything jointly, and the TOI adapts per individual. We got repulsive neighbors, part of the network that can add additional signal to the data. And the imputed values can affect each other. So this propagation through the cluster is what KNN structurally cannot do. KNN is a local independent operation, but voting game model is a global coherent optimization over the entire network in a simultaneous way. So when missing instances are forming a cluster, the coherence is the mechanism that produces accuracy gains. So in summary, the voting game model generalized KNN when observed features become mandatory or forbidden. Missing features become free choices, and join imputation through the MILP produce a globally coherent imputed dataset. On six out of the six benchmark datasets, our voting game models outperformed the KNN with the best gap reaching 8% on tic-tac-toe. And last point, the endogenous threshold provides a individual level optimal neighborhood size. So for the next slide, we can talk about the Glasgow application, which is the applications for the inverse voting game, where we're going to discover the peer influence network. Thank you for watching and see you guys in the next lecture. Bye bye.